Perfect. Welcome, everybody. My name is Jenny Wang. I have not had the pleasure to meet many of you yet. I am a new assistant professor at psychology and the Center for Cognitive Science. I primarily study infant and children's understanding of numbers and math. And today it is my great pleasure to introduce Dr. David Barner. Dr. Barner is a professor in the Department of Psychology and Linguistics and the Center for Research in Mathematics and Science Education at UC San Diego. And before going to UCSD, he went to Harvard for his PhD, working with Dr. Jesse Snedeker and Susan Carey. And he has been recognized by many as a great scientist, as a great teacher, as a great mentor. And he has made great efforts to bring cognitive science to the public, such as his fabulous and famous online course, The Science of Parenting, which I definitely learned a lot from as a new parent. His research is interdisciplinary in nature, cutting across cognition, linguistics, child development, philosophy, anthropology, and behavioral biology. We will hear about one of many lines of his research today, focusing on the origins of our concepts of natural numbers. Thank you, and please join me in welcoming Dr. Barner.
Okay, thank you. Can everyone see, let's see here, I have to figure out my Zoom setup. Can everyone see my screen okay?
Yes.
All right, great. Well, first of all, I just want to thank you, Jenny, for introducing me, and especially as your first speaker introduction. I appreciate that. As I said, I know how nerve-wracking that can be. I'm coming to you today from British Columbia, Canada. I decided that since we can work remotely, I would do it from my home and native land. So I'm up in BC right now, staring out at some mountains on Vancouver Island. So it's quite a nice setting. So anyway, thank you again for inviting me. And I'm especially happy to see all these folks that I know who the talk was designed for. Recently, I've been thinking a lot about how to integrate some of the work that we've been doing with ideas that have come out of Rutgers over the years, including work by Rochelle and Randy, and some of the challenges, of course, that some of the conceptual challenges that are faced by work that I've done that Jerry Fodor first described many years ago. And so I can't say that I'm going to address all of these challenges today, but I'm going to try to give a structure for how this might take place. And so what I'm going to do is I'll talk about the case study of integer concepts. And what I'm interested in today is what we can say with certainty might be innate about these concepts. And I'm going to start with a particular type of set of facts that I think are most difficult to explain just on any view. So I'm going to show you a couple of videos of my daughter, Anouk. One of them is when she was about 2.5, and then the other is a number of years later. She's about 9 years of age. So let's take a look at this first one when she's about 2.5.
4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
That's great. Can you count any higher?
11, 12, 13, 16, 17, 16.
Great. Thank you, Anouk.
Okay, so you can see Anouk at 2.5. She's a pretty good counter. She can count up to about 13, 15, 16, something like that. And then she kind of starts jittering around a little bit. At this point, she's got a finite memorized count list. So that's about where it ends. There aren't any rules there. If you ask her to count sets, she's pretty good at this, but makes various different errors. If you ask her whether numbers keep on going after the point that she can count, she might say that there's big numbers like 100, but at this age, kids like her insist that numbers have to stop at a certain point. And actually that's there are studies like that going back to the 80s, led by Rochelle and some of her students, people like Evans and Hartnett and so on. So Anouk has a finite procedure and a belief that numbers are finite, but eventually she comes to believe that numbers are infinite and that they're governed by rules. So here she is at around the age of 9.
Okay, so do numbers ever end, or do they keep on going forever?
They keep on going forever. We can only write so many numbers, but there are ways to go in like decimals and fractions. The fact that you can keep on adding something over and over and over again, that would have to mean that there's an infinite amount of numbers.
Okay, so here what's interesting is you can see that first of all, she thinks numbers are infinite. And second of all, the way that she justifies that belief is she appeals to different types of rules or properties of numbers, one of which is some kind of implicit understanding that numbers have a successor function, right? That you can just add one over and over and over again. So actually, this observation came up one time. We were interviewing a physicist in our physics department, and he asked her questions about the infinity of numbers. And I had no idea that she knew numbers were infinite at that point. And at the same point, he also asked her about space, and she said, in fact, he asked her, do you know anything else that's infinite? And she referred to space spontaneously. So at around the same age, she started to believe in ways that I didn't understand that various things like numbers and time and space are infinite. And so I got to wondering how that might be. How do you go from these finite procedures to the belief that numbers are infinite? Okay. So there are, of course, lots of different proposals on the table. I want to lay out some of the types of knowledge that might be implicated in these beliefs. And there are lots of different ways of thinking about this, but there are kind of two general approaches that I think are relevant in grounding out this type of knowledge of integers that children have to converge on in some form or another. One of these is Hume's principle, right? And this is just the idea that two sets are equal so long as they exhibit one-to-one correspondence. So if there's an item in the set of F, there must also be an item in the set of G, and vice versa. Okay. Another way of approaching the foundations of arithmetic is to appeal to principles like the Pirahā, like those in the Pirahā axioms, which includes, for example, the idea that every natural number has a successor, and critically that no two numbers have the same successor. And there are many different variations on these. For example, Frege was able to derive from Hume's principle in a second order logic something equivalent to the Pirahā axioms. But the problem is, so it's fine, these might be the end states that children have to represent with a counting system, but how do these hypotheses arise in the first place? So where does the notion of exact equality or Hume's principle come from? Or where might we get the hypothesis that every number has a successor? And so here, the solution for Fodor is obvious, that these types of hypotheses can't be constructed from anything that's logically simpler. And so we need to have some form of innate knowledge. And so obviously most famous in proposing this type of innate knowledge are Randy and Rochelle in their 1978 book, and then in various different forms that I won't go into great detail about here today. But the first iteration of this comes up in their 1978 book. And here's one quote from them in that book, which is, one could argue that skill in reciting count word sequences precedes and forms a basis for the induction of counting principles, but we advance the opposite, that a knowledge of counting principles forms the basis for the acquisition of counting skill. And one of those is the one-to-one correspondence principle, which in their work isn't stated in terms of sets, but in terms of the application of counting. So the partitioning and tagging and summing of items in a set using the counting procedure. And they also described a series of other principles like the stable order principle, the cardinal principle, which is just that the final tag in a count represents the cardinality of a set, the abstraction principle, that we can count anything, and order irrelevance, that you can tag things in any order and get the same outcome with the same content. So this is one kind of nativist alternative. And if you assume these principles as being available innately, then it's not difficult to get most of what a Nook has at the age of 9. So there are various different kinds of revisions to this. The most recent one that I won't get to entirely, but we can talk about at the end, is the Leslie et al. Proposal, which builds in some of this in slightly different ways than Rochelle and Randy had originally proposed. What I want to do here is, rather than going through the last 50 years of work on this and the various different challenges that were posed, I'm just going to show you a couple of behaviors of the type that people have argued are difficult to explain on this type of account. My reading of this is that it's not actually problematic for reasons that Randy and Rochelle pointed out, but that still we probably can construct a simpler hypothesis than what they proposed. So one of the types of challenges comes from this type of behavior. This is my neighbor Lorenzo. He's about 2.5. And what I do in this task, in this video, is I just ask him to give me different numbers of things, and you'll see what he does.
Could you give me one block and put one block into my hand? Can you give me one block? All right. Thank you, Lorenzo. Okay, now I have another question. Can you find 2 blocks and put 2 blocks into my hand? Can you find 2 blocks? Wow, good job, Lorenzo. All right, here's another question for you. Can you find 3 blocks and put 3 blocks in my hand? All right, is that 3 blocks, Lorenzo?
Uh-huh.
Yeah? Do you know how to count those and make sure? Can you count?
1, 2, 3.
Is that 3?
Yeah.
All right, good job.
Okay, so what you can see here is that when I ask Lorenzo for one thing, he reliably gives me 1. When I ask for 2 things, he gives me 2. But the problem is that when I ask for 3, he also gives me 2. And so this is very typical. If you can test hundreds and hundreds of kids and you find something similar. The thing I want to draw your attention to here is first just that set of behaviors, that if you ask kids to give you sets, they can construct them, and they begin by giving you 1 and then 2 and so on. But also that at this age, the counting procedure isn't deployed accurately or usefully, and various of the principles that Rochelle and Randy described are violated, or at least they aren't deployed in a way that's useful to getting the right answer. So there are lots of reasons why that might be that relate to competence and performance, for example. So we have to dig a little bit deeper. I'll show you one more video of this type. Okay, this is another child, and you're going to see something kind of similar here.
Okay, let's try another one. Okay, you ready?
4.
Can you put 4 bears on the plate?
Yeah.
You guessed it. It's 4 bears.
This is asleep.
And that one's asleep.
Yeah.
So what about the other ones?
4, 5, 6, 7, 8, 9, 10, 11, 12, 14. Those are not 4 bears yet. Those 4 bears? 1, 2, 3, 4, 5.
So is that 4?
No.
Can you fix it?
Yeah.
Okay.
And just 4.
I don't know.
1, 2, 3, 4, 5, 6, 7.
So is that 4?
Yeah.
All right, great job. Okay, so let's try another one, okay? So can you put 3 bears on the plate again?
Yeah. 1,
Okay.
1, 2, 3.
So that's 3?
Yeah.
All right, awesome. All right, let's try another.
So this is really interesting because you can see that when this child is asked for 3, they have no difficulty. In fact, the previous trial was 3 and they had succeeded at that as well. So this child can give 3 objects when asked, but then when asked for 4, not only can't give 4, but doesn't know how the counting procedure that they execute relates to that cardinality. So when they count, for example, 5 items, instead of subtracting 1 at the end, they add 1 more and then count again, and then insist that a count of 7 satisfies a request for 4. Okay, so they're failing in a number of important ways to understand how counting represents cardinality here. Okay, so that these types of behaviors that I just showed you have led people to propose stages of number word learning that look quite different, where counting is one of the last things that kids figure out. And so this is based on work by Karen Wynn originally, but you can see similar data going back to Schaefer et al. In the 1970s. And the idea is that initially when kids first start learning, so if you look at the video that I showed you of Anouk, they recite some kind of partial count list. They use it somewhat like a song, an unbroken chain, like you saw with the child that I just showed you. But they can't give you any number of objects reliably. So even if you ask them for 1, they can't do that reliably. Then sometime later, kids reliably give you 1, but can't reliably give you larger sets. And then some months later, they can reliably give 2, but not larger sets. And then they can reliably give you 3 some months later and not larger sets. So these are kind of bounded stages that kids are purportedly going through. All the while, they're reciting the count list. They're learning to execute this one-to-one procedure. Some of these kids can tell you how many things are in a set via counting, but they can't give you that number of sets when they're asked to. And it's only at around the age in the US of 3.5 or 4 that kids can point and count, tell you how many, but also use that procedure for constructing sets and giving them in the type of task that I just showed you. Okay, so I've contested just about every part of this story that I just told you in different forms. I'm not going to dwell too much on that here. One thing I'll say is that we have evidence that these stages are reliable. So the overall reliability of this framework is quite good if you do retest reliability within subjects, although the individual stages are not necessarily that reliable. So 1 knowers and 2 knowers are highly reliable. 3 knowers, 4 knowers, 5 knowers, not at all. In fact, they may not even be real stages from what I can tell. But that transition to CP knower is highly, highly reliable. If you test children who are bilingual in this paradigm, test them once in French, once in English, they have totally different knower levels for 1, 2, 3. So they learn those completely separately in their 2 languages. But the counting part is exactly the same in 2 languages. So if you can count accurately in French, then you're almost certainly able to count accurately in English as well. Okay, so these early stages and the transition to being a cardinal principle knower look like they're quite different. And there's lots of evidence, I think, for that at this point. Let me show you a couple pieces before I dive into Hume's principle and the successor function. One of these is that you see lots of finite systems where there aren't counting procedures cross-culturally. And so these are mainly documented by anthropologists. There's some more recent scientific reports of these as well. You even see them in places like Watership Down, where I think this idea is best characterized by Richard Adams, right? So he invented this language called Lapine, and in Lapine, they have a number system up to 4. And anything beyond that is just the other or frère, which is the basis for the protagonist's name, Fiver, which just meant the runt of the litter. So you see lots of cases of languages that don't have words beyond 3 or 4, okay? That's one bit of evidence that there's something different about acquiring a counting system in 1, 2, and 3. Another is that you see in various different languages that there's a relationship between number morphology and learning 1, 2, and 3. So we find various different morphological systems that have, like I just showed you, that have morphemes that are loosely related to representing sets of 1, 2, and 3. So in English, we have a singular plural distinction, which doesn't perfectly relate to the one versus many distinction, but is highly correlated with it in usage. So if we say there is one cat, we use the singular. If we say there are two cats, we use the plural. And so some people have proposed that just this singular plural distinction might be a clue to the fact that 1 and 2 differ in meaning. And in fact, what you find is that in singular plural languages, children are faster to learn the meaning of the word 1, perhaps because it's used in singular contexts, right? There's a type of syntactic bootstrapping, compared to languages like Japanese and Mandarin, where there is no obligatory singular plural distinction. You also find this in languages like Slovenian, which have a singular plural and also a dual morpheme, which is represented throughout the sentence. So we've done work in Slovenia, a number of studies with collaborators, RuCCS and Lanko Marušek, where we looked at these types of languages. I'll show you a couple of them, some of which have a dual represented throughout the sentence. So here I have a sentence, 1 red button is lying on the table, and then another 2 red buttons are lying on the table. And you can see that the dual is represented in the adjective red, in the noun buttons or button dual, in the verb are lying. So really robustly throughout the sentence every time you refer to sets of 2. In these languages that have a dual, what we find is that kids are faster to learn not only the meaning of 1, but also the meaning of 2. So here's a plot of English kids, okay? And on the x-axis, you can see different age groups from 24 months all the way up to 60 months. And then on the y-axis, you can see the percentage of kids who fall into these different groups. Kids who are non-knowers, who don't know the meanings of any number words, who are 1-knowers, who know 1 and 2, who are 2-knowers, who know 1, 2, and 3.
Finally.
Who know 1, 2, 3, and 4, or who are cardinal principle knowers. So these are the kids who can count and give any set within their count list. And what you can see is that at the earliest age range, all of these kids are non-knowers. And then you have some 1-knowers appearing, some 2-knowers, some 3-knowers, some 4-knowers. And then by the end of this age range, every kid is a cardinal principle knower based on the criteria that I showed you before. If you look at Central Slovenian in Ljubljana, what you see is various differences. First of all, most salient, because it's in blue, is that a very high percentage of kids in this group are diagnosed as 2-knowers. In fact, about half of the kids at every age range are 2-knowers, which is the largest percentage of any group of any data set that I know of, including Chinese languages, Japanese, US data sets, et cetera, et cetera. Second, these kids are almost never non-knowers at the earliest age range. So they are faster to acquire the meaning of the word 1. And finally, by the end of the age range, 60 months, they're not as likely to be counters. Okay, so they're much less likely to be cardinal principle knowers. So they're faster to get started, but then they just kind of stop at 2. Okay. So what we concluded from this is that the reason that they're faster has nothing to do with counting experience, but it has to do with the informativeness of the singular dual system. So simply hearing the words 1 and 2 used in singular and dual morphology speeds the acquisition of those number words for these kids, but doesn't impact the rate at which they learn the counting principles. And in fact, there's a couple of additional pieces of evidence for exactly this. One is that if you look in Slovenia, there are dialects of Slovenian that have the dual, like in Ljubljana and Slovenska Bistrica, those are dual dialects. But if you go south to Nova Gorica and Metlika, those dialects don't have a dual. And what you find is a difference between the rate at which kids learn 1 and 2 in the dual dialects and the non-dual dialects. Okay. Second, that difference is predicted by whether or not the children produce the dual. in their dialect. Okay, so if you show them sets of objects and just say, what's on this card, they'll use the dual for sets of 2 in these dialects and not these dialects. And whether or not they know the meanings of the words 1 and 2 is predicted by that ability. And third, that those differences are not predicted by their counting abilities. For example, how high they can count or how much training they've received in counting procedures. So if you just ask kids to count as high as they can, what you see is in the US, okay, so this is this black line, by the time kids are 5 years of age, they can count to about 40 or 50. In all 4 of these Slovenian dialects that we studied, there's no difference between them in how high they can count, and they can almost not count at all until they're about 3 or 3.5 years of age. And even by the age of 5, they can only count to 10 or 20 maximum, okay, which is significantly lower. That counting ability is unrelated to the learning of 1 and 2, but it is related to learning a cardinal principle in all of those languages, okay? So the best predictor of whether or not they know 1 and 2 is comprehension of the dual, which you can measure in various different ways, by their production of it, like I mentioned before, or by their comprehension of the dual, where you just say, put dual buttons in the circle. That's correlated with comprehending 2 and 3 and so on. Okay, so this is, I think, another strong piece of evidence that there's a dissociation between the acquisition of small numbers and the acquisition of counting principles. I showed you that in the knower levels, in the acquisition of bilinguals, and in the acquisition of these different morphological systems and how they dissociate from counting. So should we conclude based on data like this, these stages and these dissociations, that nativists are just wrong about the innateness of number? Well, I don't think so. I think that actually the core ideas in the original proposal are right, but maybe just aren't specific to counting procedures. And instead, what I want to describe today is a hypothesis where the content that's related content, such as the availability of exactness as a hypothesis, is innate, but also the ability to compose numbers, the actual symbolic forms, and generate ever larger numbers is an innate capacity, and that the composition of these two gets you some of the core properties that we're interested in. So first of all, I want to describe the hypothesis that exact number is innate, but that it's constrained by capacity limits, and in particular by a parallel one-to-one partitioning procedure. This is something, again, if you go back to Gelman and Gallistel, 1978, is described, and I'll show you exactly how. And then the second thing that constrains this capacity is a finite sequence memory, which they also describe. In part 2, I'm going to talk about or propose that counting is a real cultural innovation. So the actual count lists themselves are quite contingent, highly variable cross-culturally. But what they have in common is a generative and sequential Markov procedure for expressing innate one-to-one knowledge that otherwise can't get out into the world. Okay, so let's start with exact equality in Hume's principle. So what I started out by saying is that you can characterize this, you can characterize exact equality via Hume's principle and the idea that two sets are equal so long as they exhibit one-to-one correspondence. But there's a couple of problems with executing this, right? So how do you verify that the sets F and G are equal? Well, you need some kind of partitioning procedure to do this, right? You need to be able to take an item in F and align it with an item in G, and then set those aside so that you can move on to the next pairing, and set those aside so you can move on to the next pairing, and so on. The problem is humans can only accurately partition large sets via a sequential procedure, like the one I just described. And the second problem is that from what I can tell, Innumerate humans only partition sets in parallel, or at least that's their preference. And what I'm going to argue is that it's not because they can't do it in a sequential procedure, but that this is just not at all a hypothesis that they entertain by default. Okay, so there's various different bits of evidence that pre-verbal humans can compare and evaluate small numbers using one-to-one correspondence. This is a claim that's made in the early papers by Lisa Feigenson and Susan Carey, that when kids do a manual search task or when they do a forced choice, they're executing a one-to-one correspondence between either sets or between mental symbols and items in sets. And that because one-to-one correspondence in these models is a parallel representation, so we're comparing 3 items here to 2 items here in parallel, rather than 1 item here and 1 item here in sequence, these types of representations ultimately crash due to working memory constraints. So that's one type of representation that's been proposed that might have the content of one-to-one correspondence and possibly even exact equality, although I don't think it does, but I can't go into that here. Another system, of course, is the approximate number system, which is also capable of representing the equality of small sets exactly. Okay. I'm not going to go into a lot of detail today trying to differentiate which of these two systems might be involved. I think actually both of them can describe quite well the learning of small number words and everything I've said up until this point. What I think is much more controversial is whether the approximate number system can provide the content of larger numbers, or at least whether that's the way that kids get there. So one way that this has been studied is in Innumerate indigenous groups. So many of you probably know this work by Peter Gordon and various follow-up studies, where what Gordon did is he just showed members of this group, the Pirahā, an Amazonian group, a set like this. This is 5 batteries, and then asked them to just make their set the same, and not more complex than that. And he also showed them an orthogonal match task like this and a variety of other tasks too. I'm just going to focus on these 2 for now, because already on these relatively simple tasks, he found that the Pirahā didn't match exactly beyond sets of 3. Okay, so here you see that for targets of 1, 2, and 3, they were perfectly correct, but then for larger sets, they approximated. And for orthogonal line matches, they approximated even after sets of 2. And what Gordon argued from these data is that therefore integer concepts must depend on language, because when tested on a test of one-to-one correspondence, the Pirahā who are enumerate failed, whereas numerate groups succeed. Okay. There's various different attempts to replicate this. Actually, Frank et al. Did not replicate this study. That's the top line. They found relative success for much larger sets on this parallel set match. Everett and Medora did a 3rd study where they replicated Gordon, and they argued that Frank et al. Had tested participants who'd been explicitly trained to count by missionaries. And in fact, I think maybe one of them had been involved in training that group. So there was a fair amount of controversy regarding what the Pirahā actually can or can't do. And I think if you look across the literature, you see similar amounts of controversy in other enumerate groups, of which, there are many of these studies now. There are kind of semi-numerate Nicaraguan Sign Language users. And so this is one study that showed kind of similar results to Gordon in late counters and non-counters, where there's success for smaller numbers and then approximation for larger numbers. Work in the Munduruku, who, despite having a body counting system, also generally approximate for sets larger than 3 or 4, and so on. Okay. So one of the problems with this work is, aside from the fact that it's very difficult to go and replicate and dig deeper, and there are also methodological problems. It's hard to do the work there. It's hard to use robust measures. There are just many different difficulties. Another problem is that we're trying to compare members of, for example, the Pirahā to speakers of English in US suburbs, right? It's very difficult to make these types of comparisons because there are just many, many, many differences between these groups, aside from the fact that one can count and the other can't. One of these differences is that numeracy isn't just one thing, right? And so we don't know what components of numeracy might contribute to differences on these tasks. But as I just showed you, in children, we can begin to carve out different components of numeracy that emerge at different points. So we see the memorization of a count list begin very early on, where kids can count to, maybe 5 initially and up to 70 by the time they're 5 or 6. They start to learn a one-to-one counting procedure very early on, as Rochelle's work showed in the 70s and 80s and 90s. And then there are also these kind of stages that I showed you where they learn the meanings of 1, 2, and 3, where they reliably use the cardinal principle. And then at some point, like a Nook, they start to judge that numbers are infinite. And it just keeps on going after that, right? Numeracy continues as long as you want to keep studying mathematics. So we can ask which of these different parts might best predict judgments about exact equality and one-to-one correspondence. So one student in my lab, Rose Schneider, led a series of studies on this question in collaboration with Roman Feynman and Eric Brockbank. And what she did is she just replicated the work of Gordon and asked, do we need to go to the Amazon in the first place to do these studies? And the answer is no, because you find the identical thing in young children. So this is fantastic news for anybody who wants to study these phenomena, because we just no longer need to go into the jungle and risk the mosquitoes and so on. And so what she did is she gave them the same task, this parallel match task. She also gave them an orthogonal match. And kids were just asked to make their sets the same, okay, in this first version. They were trained on 1 and 2 and then tested on 3 through 10. They were told they couldn't count in this first version. They were also tested with that give a number task, where we see, do they know 1, 2, 3, or can they count and accurately give large sets? And we gave them an assessment that rated on a scale of 1 to 3 how accurately they could use the counting procedure, which is a separate thing. So can they count and place words in one-to-one correspondence with objects, and can they say how many there are at the end? And remember, that ability is separate from the ability to count and then give that number accurately. So there are lots of kids who are called, say, 2-knowers, who can count and say how many there are, but can't give you that number in the give a number task. So this gave us a measure of their mastery of the counting procedures and whether it's related to this one-to-one procedure. And what we find is just exactly what Peter Gordon found. So with one interesting difference, which is that we have kids who can count, okay? So these orange lines are subset knowers. Those are kids who know 1, 2, and 3 only, but don't know larger numbers. And you can see that for sets of 3 and 4, they're pretty good at 75% for sets of 3, slightly worse for sets of 4, but for 6, 8, and 10, they have very poor accuracy. And another plot of this data shows that they're approximating. And on the orthogonal match, right, where the sets are aligned like this, you see a similar pattern with a slightly depressed behavior. Okay, so not quite as accurate. In kids who are classified as cardinal principle knowers, who are counters, you see actually very similar thing, but just that they're a lot better. Okay, so you see for 3 and 4, they're very accurate in both the parallel and the orthogonal, but they're approximating for larger numbers in both cases. But there is a difference in this parallel match task. So notice the difference between parallel and orthogonal. They're more successful here than here. And there's a couple of different reasons this might be, which I'm going to get to in a moment. One of which is that they might just be better at approximating as they get older. So this all could be explained by just an improvement in approximation over time, or a sharpening of the approximate number system. Now, I want to point out, this is important, that these behaviors are significantly related to the how many task. So the ability to point and count in one-to-one correspondence. But that's only when you exclude the distinction between subset knowers and CP knowers in a model. As soon as you add that to a model, the how many task is no longer predictive. Okay, so that's going to be important later. Let's see. All right, right. This is just kind of histogram showing the frequency of different responses. And you can see that for the cardinal principle knowers, the modal response is correct for 3, 4, 6, 8, and 10. But for subset knowers, it's correct for 3 and 4, but then stranger things happen for larger numbers. But overall, they're centered around the target, and they have a heuristic of giving all, right? So some of these kids just give everything in the set. And you see the same type of behavior for orthogonal too. Okay, so there's lots of evidence here that the approximate number system is playing a role in this task, like Peter Gordon suggested. But there's also evidence that counting plays a role and that it's sharpening the behavior, especially in the parallel case. So the question is, why is this? Well, one of the major critiques of Gordon's work is that the Pirahā don't have numbers, and there's no way of telling them that this task is about number. So maybe they don't even know they're doing a number task in the first place, right? So Lawrence and Margolis point this out. How do we know that the Pirahā are even doing a number task? So one of the things we do in our next experiment is just tell kids, without counting, can you make the pond have the same number of fish as my pond? And trust me, cardinal principle knowers know what number is, right? They know what counting is. This doesn't change anything in the data whatsoever. Okay, so you see in the first study and the second study, identical behavior for CP knowers, cardinal principle knowers, and subset knowers for both small sets and large sets. There's absolutely no impact of telling them that this is about number. Also, this behavior is not changed if you describe this as a sharing game. We know that kids of these ages care a lot about giving equally, and if you restrict these games to small sets, they'll always give equally. But what we find here is that when we make this into a penguin sharing game, so this penguin collected a bunch of fish, and we want to give this other penguin a fair number. So they collaborated, they fished together, they equally own these fish. When the child is asked to help them share fairly, what Rose found is just the same pattern of data again. Okay. In fact, if anything, the counters are slightly worse. And same thing for the subset knowers. There's no statistical difference at all when you ask them to share. Okay, so again, this is a case where number really matters, where equality really matters. And they just have no idea that you should use a one-to-one procedure to get there. We also wanted to rule out that the cardinal principle knowers might be secretly counting. So this is important because one reason why the cardinal principle knowers might be succeeding is because they're actually counting and getting 6 and 8 and 10 right more often just by virtue of using that procedure, but not because they understand anything about one-to-one correspondence. So first of all, we asked them to do this first phase where we asked them to make the pond look like the target pond. And then we covered the ponds and we just said, how many fish are in my pond? Okay. So if you're counting, you should know, right? And in phase 3, we asked, we said, count and see how many there are. So we showed them, we let them count, and then we asked them to remember how many there are. That's just a memory check to make sure that they can remember their count. And what we found is that, first of all, most kids, or at least half of the kids, didn't try to guess any number at all. They had no idea what to say. 13 of those kids who guessed, of those, only 2 were correct, okay, out of 28. And the 2 who were correct hadn't matched their sets correctly. So they actually guessed correctly, but just by chance, right? When they actually did the set matching task, they had matched incorrectly. So that's another piece of evidence that counting isn't at play here, but that the kids are really getting one-to-one correspondence. Probably the best evidence that one-to-one correspondence is emerging is if we try to model these data. So one alternative hypothesis is that the kids are approximating. So what you can do is you can ask, is there any value of a coefficient of variation, which is consistent with an approximation strategy that can fit the data of the cardinal principal knowers? And so these are all CP knower data and simulated data here in gray. And what you can see is that the CP knower data are very peaky, and they have this kind of distribution as well. But if you just take the COV of these data, okay, of the CP knower data, you can't find any single value of the COV that gets you both this distribution and the peakiness of the CP knower data. And in fact, what best fits the data is a hybrid model, where you assume that there's some number of, there's some error-free strategy plus the COV that we estimated from the data. So if you estimate the COV, it's about 0.32 for this data set. And it turns out that about 30% of trials, if you assume that those are just using an exact matching or one-to-one correspondence strategy, the rest of the data are fit very well by the approximate number system. So this we take to be evidence that there are really these two strategies combining. One is a one-to-one correspondence, which emerges after kids become counters, and the other is approximation. So infants, innumerate adults, children can do one-to-one correspondence for small sets. When kids learn to count, they seem to get better at doing one-to-one correspondence for larger sets. But although this improves one-to-one, it's still far from perfect. Most cardinal principal knowers are only about 50% correct on those large sets. So there's a continuing process of change after the CP stage. Okay, so if there's a couple puzzles here. So if humans can do one-to-one for small sets, why do they fail for large ones, first of all, right? And this is addressed in part by a proposal that Randy and Rochelle made in their book, which is that you require that counting provides a partition procedure, right? So kids and innumerate adults seem to use a default of a parallel partition. They just grab sets that look the same. So they seem to be approximating, right? Counting creates a sequential partition. So each step in the partition generates a unique label, and you don't need to remember what happened at the previous step. So it's memory-free. It's a memory-free Markov process. So an entire sequence of, say, for example, 80 things is summarized in one symbol at each step along the way. So the question is, why do some CP knowers fail then? Because they have a sequential procedure like counting. So why is it that they continue to fail for some time after they learn how to count? Well, as I noted already, there is a one-to-one counting procedure that even much younger kids have, and they don't understand the significance of it with respect to cardinality. One thing we know about Hume's principle is that there are actually two components. One of them, from an epistemic perspective, is just understanding one-to-one correspondence itself, right? Knowing how to deploy that procedure and its availability. But the second is knowing that one-to-one correspondence guarantees equality, which is an entailment of one-to-one correspondence, but isn't necessarily an obvious entailment to the learner. It might be something that you have to discover, like many mathematical properties, right, that are entailments, but not known automatically by a learner. So everything that the child knows so far is compatible with a finite number system. So the question I want to end with is, where does the child's intuition that numbers are infinite come from? And I hope that I can also tie up how one-to-one correspondence gets related to an infinite successor function. Okay, so here's an idea that Susan Carey and Barbara Sarnecka lay out, which is sometimes called a bootstrapping hypothesis. And this, they say the cardinal principle is often informed
I lost the audio.
I lost everything.
There we go.
Yeah.
All right. I don't know what happened.
Okay, I got it back.
Okay, so their alternative idea is that it's something a bit more profound, that it's a principle stating that a number's cardinal meaning is determined by its ordinal position in the list. So knowing the cardinal principle means having some implicit knowledge of the successor function and an understanding that the cardinality for each number is generated by adding 1 to the cardinality for the previous number. And actually, you see something similar in John Stuart Mill. So actually, it looks very, very similar, in fact. So he says, you know, we may call 3 is 2 and 1 a definition of 3, but calculations which depend upon that proposition don't follow from the definition itself, but from an arithmetic theorem presupposed in it, namely that collections of objects exist, which while they impress the senses thus, may be separated into different parts. This proposition being granted, we term all such parcels 3s, after which the enunciation of the above mentioned physical fact will also serve for a definition of the word 3. So he defines small number words in terms of the same types of representations that Sarnecka and Carey want to define them in terms of, which is some kind of parallel individuation. And then he goes on to say that learning these relations between 3 and 2 and 2 and 1 are the basis for an inductive inference to the rest of numbers. And so we get the successor function from noticing relations between directly observable small sets about which we have certainty, and then we make an inductive inference to all numbers, exactly like Sarnecka and Carey propose, where there's a successor relation between items and a successor relation between words. Noticing this analogy gets you the implementation of the successor function in counting. Okay, so the question is this right? So here's Lorenzo again. He's now at about 3.5 years of age. And so I give him a task that Sarnecka and Carey used to assess this idea. Oh, sorry, I have to reshare with audio.
Can you do me a favor and can you find 6 pennies and can you put 6 pennies into that cup?
I'm gonna count them.
All right, you can count.
1, 2, 3, 4, 5, 6.
Awesome job. So how many pennies are there in there now?
6.
6 pennies. All right, now watch what I'm going to do. All right, I'm going to put 1 penny in here. How many pennies are there in there now?
1, 2, 3, 4.
Okay, do you remember what I did? How many pennies did you put in there at the beginning?
6.
All right, now I'm going to put 1 more in. Watch. Okay, now how many are there? Are there 7 or 8?
8.
Okay, so Lorenzo at this age can accurately count, no problem. He can count very large sets accurately. He can remember the outputs of his count, but what he doesn't know is why it works. So he doesn't know that as you go up 1 in the count list, you add 1, or that as you add 1, you go up 1 in the count list, right? So he can execute this procedure from 1 over and over and over again, but he can't, from the middle of the count list, tell you what the output is if you add 1 item. Okay, despite the fact that he can tell you what the next number is in the count list. So that's not his problem. And this is what Sarnecka and Carey showed. They showed that CP knowers are better at this task than subset knowers. But what they didn't show is that the way you become a CP knower is by learning that principle, which is what their claim was, that you, like John Stuart Mill said, you notice things about 1, 2, and 3, and you generalize that to all numbers, and that makes you an accurate counter. Kate Davidson at Harvard, she was at UCSD for a while. She showed this by just asking a bunch of cardinal principle knowers to do this task. So here are kids who can count almost up to 20. These are all counters. And on a task where they're asked about 4 and adding 1, the modal response is most kids are just a chance on this task, okay, even for very small numbers. If you ask kids who can count almost up to 30, even for very small numbers like 4 and 5, they're a chance at this task, okay? And that's also true for medium-sized numbers like 13 and 15. Some of the kids have begun to get it at this age. This trend continues up to the age of 5.5, at which point kids can do this for any number in their count list. Okay, so there's some kind of generality where they can do this up to numbers like 100, no problem. One question that came out of this, so work by Pirahā Chung, who was a visiting scholar in my lab, was when this resolves and why, and what's going on when kids figure out that this rule can apply anywhere in the count list. So she found that kids can apply this +1 rule by around the age of 5.5, and that it's still some 6 months later that kids claim that numbers are infinite. Okay, which is, by the way, around the same time that Rachel showed in her early work on infinity as well. So kids don't seem to understand that there is a generative process for constructing ever larger numbers until they're around 6. At least they can't declaratively say that. But this makes sense that they can't declaratively say it if they don't have a +1 rule that's fully generative until that age. She also noticed that this is strongly related to how high kids can count, which isn't surprising, because as they age, they become better counters. In Gelman and Gallistel, they argue that human memory can't readily store stable, recallable lists of items when there's no generative rule underlying them. So part of the counting procedure part of becoming a competent counter must be learning a generative rule, right? And so Pirahā hypothesized that the reason why counting experience is related to infinity is because children notice a recursive syntactic rule that allows them to generate ever higher numbers, but also supports a purely inductive inference that numbers never end. Okay, not fully supported, but this is an inference that kids nevertheless make. And so we've investigated this in various ways, and in my final couple of minutes, I'll tell you about one way. So this was to look at languages like Cantonese. Okay, so Stigler and Miller looked at Cantonese and argued that Cantonese kids are faster to learn how to count and do various different arithmetic tasks because of the transparency of their count list relative to English. I'm going to show you that that's actually not true. They're not any better than English at all, and that it's just probably a sampling error. But Cantonese is very transparent. So the numbers 1 through 9 are irregular, but then 10 is sup, and 11 is just 10-1, 10-2, 10-3, 10-4, right? And then when you get to the 20s, you see 2-10-1, 2-10-2, 2-10-3, and so on. It's highly regular all the way up to 100. However, there are also languages like Hindi where you have irregularity up through 9. A word like the word 10 is das, but then 11 is not predictable at all from 10 and 1. 12 is not predictable at all from 10 and 2, and so on, which is not to say that there aren't rules, but there are many irregularities. So if you just look at 5, it's panch, pandra, pakis, pentis, right? And if you look within each of these decades, you'll see irregularities in how the decades are expressed. So Hindi is a highly irregular counting system, as is Gujarati, a language where we went and a language that we studied in Western India. So Rose conducted this study where she compared kids in Hong Kong who are learning Cantonese, kids in the US who are learning English, kids in Slovenia, which is also a highly regular counting system, similar to English, actually less regular than Cantonese. And then we looked at 3 groups in India, children learning Hindi, kids learning Gujarati, and then kids who are learning English in an English medium school. And so we were in Vadodara, India, which is in Gujarat province in Western India. And we tested the devil's number of kids across these different groups, 3.5 to 6.5-year-old kids, and about 100 kids per site. So a couple of things to notice here in the data. First, if you look at the x-axis, this is the kid's initial highest count. The y-axis is their final highest count. And you can see that those numbers are identical for some kids. So in other words, they count to 30, and then you ask them, is there another number after that? And they say, I don't know, I'm done. Okay, so those are these kids, and the light dots. their initial highest count and their final highest count are basically the same. Okay, and so these kids here are kids who can continue counting if you prompt them. And in particular, these kids are highly likely to count to 19, 29, 39, 49. So they don't know the decade term, but they do know the rule for counting up from decades. So they know the unit rule. So if you tell these kids the number after 29 is 30, then they count all the way up to 39. Okay, so these kids we called productive counters. And you see that about half of the Cantonese kids are productive in this way, a quarter in Slovenian, almost 40% in US English. And if we look at Hindi and Gujarati, we see that almost all of the kids have just a memorized count list. So if you prompt them to go beyond their first count, most of the kids can't do anything, right? And the places that they stop are arbitrary in the count list. They don't stop on the decade transitions, although they work a little bit differently in these languages. But if you test kids who speak English in India, they look like the English-speaking US kids, right? Exactly the same. Just suggesting that it's the syntax of the count list that is restricting the productivity of the rule that the child can learn. So now the next question is the point at which you acquire a productive rule predictive of anything else? And within each of these languages, it is. Okay, within Cantonese, Slovenian, English, and Hindi, Gujarati, there's just not enough productive kids to measure. You see that whether or not you're a productive counter is related to whether or not you know that if I add one to the set, you should count up one. Okay, in other words, that measure of the successor function. But also you see cross-cultural differences. So in these more transparent languages, kids are significantly better at that task, the adding one task, than in the more opaque languages, which is perhaps not surprising given what I just showed you. So the next question that we'd like to ask is whether kids' judgments about the infinity of numbers differs across these cultures. We haven't done that yet, although we have done this within the US. And what you see is that the productivity of counting, so the ability to continue counting up when prompted when given those irregular decade items, that ability is predictive of whether or not kids think numbers are infinite. So if you look at non-productive counters, virtually all of them think that numbers must end. But if you look at counters who are productive, you see that now about 40% of them think that numbers are infinite, which is not all of them, right? Which is compatible with Pirahā's observation that kids get the successor rule first, and then it's some additional inference that's required or observation that therefore means that numbers never end. So that it doesn't come for free. None of this does. Okay, so I want to circle back and try to answer what I think might be innate. So first of all, I think a good candidate for innateness is a concept of exact equality and one-to-one correspondence that's defined over sets, not necessarily over counting itself. And second, a syntax for composing symbols. And that what's innate isn't necessarily counting itself, but the composition, the ability to compose symbols and one-to-one correspondence that together give you something like the behavior that we see in Inuk at the beginning of the talk. Let me say a bit more about that. So cardinal principle knowers can count and give sets, but they don't know that numbers are infinite. They don't have a generative syntax. They don't even know that you can use one-to-one correspondence to assess whether or not sets are equal. So they're missing a bunch of stuff, but they do have a procedure that tells you how many there are and that allows you to construct sets that have equal numbers. And so one hypothesis is that that ability, which can be described as a relatively simple procedure, is sufficient for for creating models, right? That you can then use to notice and assess other mathematical properties like one-to-one correspondence and the successor function. So let's say that you have the ability to count and you construct a set like this. So just by placing numerals in one-to-one correspondence with items, you can say how many there are. You can say that there are 4, and you can also give that number. let's say, because you're a cardinal principal knower. Well, if I repeat that procedure, then what I end up with is, first of all, interestingly, the same numeral, but also I end up with the same number of items. And what this generates is a one-to-one correspondence between items in both of those sets, right? So counting the same set over and over again is one piece of evidence that this is true, that there's a one-to-one correspondence between labels and items, and that whenever you do a count that has the same outcome, those sets stand in one-to-one correspondence with each other. Or just counting different sets and noticing that if you add one, the outcome of the count changes. So repeatedly noticing these types of things might be evidence that labels somehow represent that the one-to-one correspondence between sets is reflected in the one-to-one correspondence between labels and sets, right? So this is one source of evidence. Another kind of piece that flows out of this is this analogy that that Sarnecka and Carey mentioned before, which is that you're in a position once you have a counting procedure and you can create your own sets to notice that as you count up one, you should add one. There is a literature on this. So Karen Fuson has a number of studies that try to train children on exactly this type of inference. And it turns out to be incredibly difficult because when you show kids, for example, a set of 5 and then add 1, what they do is they will count from 1. And if you cover the first set, like I showed you before, they don't know what to do. But it turns out that if you train them for about 2 weeks to think about the hidden set as 5 and then to do this addition procedure of adding plus 1, they can eventually get it. So just by brute repetition, that function actually is accessible to these kids. Now, the question is, what would ever justify inferring that therefore numbers are infinite? And what I tried to argue before is that it doesn't come from number at all. It comes from the use of a generative syntax. And it's not a justified belief. It's a wild speculation on the part of the child, right? That because we can compose numerals, the actual words, and because there's a rule for composing the next number that from their perspective generates ever larger numbers, there's no reason to think that that doesn't just continue indefinitely. And because this applies to number, it's highly constrained. So because this system represents numbers, which are linearly increasing, they have evidence that this isn't a cyclical process, so long as this analogy holds, right? That this is basically where I want to. I'm gonna end now because I think we're out of time. But I guess the last thing I'll say is there are lots of pieces still missing here. So if one-to-one correspondence is present, I think you have the logical basis for the integers, but we don't have an explanation of how we get an infinite number of numbers. I think that syntax might be one way of getting there based on some kind of unjustified inductive inference. The question is why children make that inference and what it is about syntax that leads them to do that. But yeah, happy to take questions. And I just want to thank my collaborators who worked on this project and also Anouk and Lorenzo for their video. Thanks, everyone.
Thank you, David. So I'm not sure if I'm supposed to be moderating the questions. So I will, if nobody else steps in, I would kindly ask everyone that has a question to either type in the chat that you have a question or raise your hand or signal somehow. I see that Karen already has a question. So Karen, would you like to get started?
Yes, this was a lovely, lovely talk. And I'm going to go way to the beginning. So I'm fascinated by the Slovenian dialects where some are non-dual and some are dual. And I couldn't help but notice that the Slovenians seem to come to being CP learners later than than say the English speaking children. And I wanted to ask sort of a trivial question, but do the speakers who are non-dual Slovenian speakers, do they look more like English speakers?
Yeah, great question. So yeah, I went over this pretty quickly, but no, they don't. They look, so all the Slovenian kids are later to count than US kids. And the CP transition in those groups is related to how high they can count. And the explanation, I think, is just this. So I remember the first day we went into the childcare centers there, and my graduate student, Jess Sullivan, was just baffled because all of the kids were 2-knowers and they couldn't count past their knower level. So the first cohort that we tested, they would count to 2. So they just hadn't been trained at all on counting, but they did know the words 1 and 2. And so why are they slower to become CP knowers? The idea is that whatever makes them 1 and 2 knowers is completely separate from the problem of learning to count, and they just don't get any training on counting.
So it's just a boring, they're not taught.
They're not taught. Even in preschool, the kids are not taught to count.
So I was wondering if there was something about being a dual learner that it works pretty well and you getting all of this evidence of it. And so in some sense, it impedes you from, sort of going the next step since the syntax is telling you.
Yeah, no, that's one of the, it's a tempting conclusion, but it doesn't seem to be the case. It's more like learning 1 and 2 are like learning, whatever, cat and dog. And that's not helpful. It has no impact on learning 3.
Okay. Thank you.
Yeah.
And I think Randy might be next, followed by Kenneth.
Okay. I reading your paper with Susan on the approximate number system, I was a little startled because you seem to think that I at least still think that it's noisy and analog. Have you been disabused of that thought?
Yeah, no, I don't. I'm sorry if I gave that impression. I don't.
Well, the paper is pretty unequivocal about it and was published in 2019.
Well, let me tell you what I think. I don't think it matters if the approximate number system is precise.
Well, it matters when it comes to equality.
Well, I don't think it does. So there's a variety. Now there's a number of people who have kind of endorsed this view that you propose, and I think it sounds perfectly reasonable. In fact, the opposite doesn't sound reasonable, that the actual representational states are approximate.
Good. That's
so
progress.
For example, what's that?
I said, that's progress.
Yeah, no, I mean, it sounds perfect. It sounds right. And, there's others like this really nice, Justin Halberta has a paper that makes similar claims. There's also Jake Beck at York, who has a really nice BBS paper that's coming out that you might be able to comment on.
Yeah, I've already put in the comment on that.
Great, yeah, it's beautiful. And so that's not the problem, I think. The problem is not the noisiness of the mental states. It's the noisiness of the relationship between the mental states and the world, right? So when we look at the behavior of the Pirahā, okay, or let's say in an approximation task, like a numeral estimation task, I have no doubt that the mental states or the epistemic state that the users are in is one in which there's some kind of precise representation, but the isomorphism between that and what's going on in the world is noisy, right? And so long as that's true, getting the meanings of the integers from that system is going to be impossible. You need some kind of procedure, right, for guaranteeing that what's out there in the world corresponds to your mental representations in an error-free way. And that's what the approximate number system, that's what makes it the approximate number system, because it doesn't have procedures, verification procedures, that guarantee one-to-one correspondence between items in the head and items in the world.
But that's because now you're reifying your hypothesis that one-to-one correspondence is what equality is fundamentally about. Now, as you well know, in a computing machine does not decide on the equality of two variables on the basis of one-to-one correspondence, right? If you ask your computer if pi equals pi, it'll tell you that yes, pi equals pi.
No.
So
Of
it
course,
does so on the basis of identity of representation, right?
right. What I'm talking, sorry. So you can talk about one-to-one correspondence as a procedure or as a property, right, of two sets. And how you establish that this property of equality is true or exists between two sets is, there's many ways. That's one of the things that we use counting
Doesn't
for.
have to be sets. We decide equality, inequality between quantities of all kinds.
Absolutely.
Like pi.
I'm sorry to interrupt. I think this discussion it's a very important one and extremely theoretical. And let's see if we can fit a few more questions in the remaining 9 minutes that we have, and maybe Randy and David can continue that discussion a little bit later today. All right.
Who's next?
Kenneth.
Who? Ken?
Hi.
Go ahead. Yeah, fine.
Hi, I came in very late to the talk. Doctor's appointment, what are you going to do? But the last point you made about the inductive saltation to infinity, right? And you suggest that this could be perhaps something like syntax doing this, right? I mean, we're now that's maybe testable in a certain sense. What exactly do we have to assume that is in that kids take in at a certain point in order to make a generalization about syntax? Okay, and so the question then is, could you find an analogous trajectory of deduction about major generalizations, so like all verbs end in ed, along the lines of this kind of leap to infinity? It's might be a way to test it.
Yeah. So Charles Yang had proposed a number of years ago something like, just viewing this as another case of morphological learning, because that seems sensible, right? The count list is a morphological system, and so if you just view if you think about the learner as encountering a data set, up to the first 20 or 30 words, they're completely irregular from the child's perspective. And then you begin to see reiteration of the unit rule, at which point, after a certain number of reiterations, you're going to want to propose a rule because it's a better explanation of the data from the perspective of a morphological learner. So that's one way of viewing it. The thing is, these kids are pretty old. They're, by the time they are treating the number system, or they get some kind of generative rule, they're around probably, anywhere between 4 and 5.5. But so the other thing to take account of is that you maybe shouldn't expect that the actual timing of that rule learning to be related to other rules, because it depends on the amount of data that you get. So you have to have had exposure to numbers above 30 or 40 before a rule is justified by the data, or it's required by the data. So, this is unlike, for example, the plural or the past tense, where you're just getting, incredible amounts of evidence for a rule from very, very early on. Here, you need to have the frequency of large numbers in the input to children is relatively sparse. Yeah, it's a great question how we could tie this to other types of syntactic learning. And one thing that we're trying to do right now is we're thinking about the Hindi and Gujarati data because it's so irregular. And what we'd like to do is look at those languages and figure out what types of hypotheses kids might be making that are not kind of normative. So they have all of these irregularities, but they might be trying to fit rules to those irregularities. And so we want to look at the errors that they make and whether they're compatible with some kind of generalization from earlier items in the data that they get. I'm not sure if that answers your question, but
yeah, well, you point out what's going to be why it's going to be difficult to model it on the basis of other morphological learning, and so I think then the question is, well, is it worth the effort to try and figure out if there's another kind of morphological learning that requires a similar amount of data before you know it, and then try to make some comparisons. I do think that given the somewhat lateness of the infinity deduction, that it may not that may be evidence against suggesting that it's truly syntactic. But that it's a matter to be settled empirically. In any case, thank you for your response.
Thank you. And the next in line is Paul.
Thanks, Dave. I wonder if you could just say a little bit about what you think the relation might be between the stuff you ended with and that Ken was just asking about, and the fact that every number has a successor principle is different than no two numbers have the same successor. And so, don't know about psychology, but if you're a logician thinking about trying to reduce the axioms of arithmetic to Hume's principle the way Frege did, those principles get proved in really very different ways, right? You actually need induction to get you that every number has a successor, and you don't need induction to get you that no two numbers have the same successor. And so I was just wondering if you think that what the kids have is at some stage that you can keep cranking these things out, but whether or not you're actually going on as opposed to doing clock arithmetic, that's just a separate question for them.
Yeah, so this is a question that's come up before in the literature, and I think Randy asked me about it in an email. And I think, so not being a logician, my understanding of this is that one way that you might solve this problem is by constraining one possibility, for example, is you get to 100 and you start over again, right? Actually, interesting things happen after 100 when you ask kids to count. So in every language that we've tested, when you get to 109, kids have no idea what comes after. And you have to tell them that it's 110. And you can see that suddenly the kids get it immediately. They're like, oh my God, there's an embedding rule, right? And then they know exactly, but what they expect is after 109, 100 and blickety, just decades all the way up, right? So the actual structure of the list is quite late, and that's true for us as well. That there's a certain arbitrariness to how bases are expressed across languages. But the question of how we know that we don't just begin, that we're not in a mod system, for example. What I said earlier is that this might be constrained by your knowledge that this is an effort to represent a linear set of cardinalities. That the analogy can get the analogy between the list and the cardinalities that you've experienced so far tell you that every that what you're trying to represent is cardinality. And so if you were to circle back syntactically, given that type of representational system, you're, I mean, it's still a possible system, right? You could still have a system that represents 101 with 1. But my guess is that the fact that these are mapped onto each other is constraining enough that kids, based on the knowledge that cardinalities can extend indefinitely, infer that or at least that they're, you can't represent the successor of 10 with 1, that therefore you're not in a mod type system. I don't know. So some people have told me that this might be enough. I'm not sure if it is from the perspective of a logician.
Well, I guess I was thinking not about that the successor 10 might be 1, but that the noise 11 might re-represent the number 1, right? That's the thing you've got to rule out to get that no two numbers have the same successor.
Yeah, right. No, that's right. So yeah, sorry for the ambiguity. Right.
I think we're at time. We have a few more questions. I apologize that I have to run to teach my class now. Thank you so much, Dave, for such a great talk. So the next in line is Mark Baker and followed by Alan Prince. But I also know that David has a meeting scheduled with Alan that's scheduled for 2:30. So I'm not so sure exactly what's the best way to handle it. I have to apologize myself for myself. I excuse myself and leave right now, but I'll give the stage to the rest of you. Thank you so much. I'll talk to you later.
I'm happy to take a couple more questions, and but I also don't want to. I'm not sure what to do. Yeah.
So I say answer the 2 questions, then you can run to your meeting if that's okay.
All right.
Whoever you're meeting with, I'm not sure.
Sounds good.
All right.
Okay.
Thanks, then. I was also interested in like the relationship between syntax and infinity, but I was thinking along about a different line. So are there different concepts of infinity then? And are you talking about a particular kind of infinity or a generalizable idea of infinity? So I was thinking there could be a kind of infinity underwritten by the approximate number system, the quantity system too. So for whatever quantity you have, I suppose you can always have more. So I have this much, and now I add some more. Not +1, a discrete thing, but still the idea that whatever quantity you have, you could always have more. Well, that could be a kind of infinity underwritten by the approximate number system.
Mm-hmm.
Is that the same kind of infinity? Does it come at the same time? The connection of that between syntax would seem a bit more remote.
Yeah. So in one paper, we proposed that the approximate number system is probably how you get started here with respect to the successor function, because it's the successor function as it's implemented in the count list is a later greater rule. And so in other words, children recognize at some point that as you count up, the cardinalities are represented by the count list are greater than the ones lower in the list. But that actually isn't something they get right away. When they first become cardinal principal knowers, they don't know that. So they might be able to count to 30, but they don't know that 20 is greater than 10, for example. But they do figure that out. But they don't know necessarily that 24 is greater than 23. So you get like kind of distance effects, right? Where it's easier for them to say that 30 is greater than 20. And so one thing that we proposed is that you might start out by assuming that numbers that are later in the count list are greater, but you might not know that the count list represents byte increments of 1. And the last step in getting the successor function is just that. It's not actually the fact that there are it's always possible to add. It's that it's always possible to add 1. So it could be that kids have some kind of sense that it's always possible to add an amount even earlier than what we estimated, which is around 5.5, because that's when they know it's always possible to add one, or rather that's when they can judge the outcomes of adding one. But despite that, the point at which they think numbers are infinite, it's around 6. There's other work that's tried to get at different paths to infinity, but they find much later trajectories. So like, notational systems like, the decimal system that Anouk referenced, kids aren't using that at 5.5 or 6 years of age. They're just beginning to learn it, but they don't know that, you can just write zeros indefinitely. There's also work by Falk. He tries these kind of neat tasks where he says, like, we're going to try to guess the bigger number. Do you want to go first or second? And kids don't know that you should pick second if you want to guess the bigger number. And so he takes this as evidence that they don't know that numbers are infinite. Kind of wild idea, but aside from that, there's not a lot. So I think there's a big space of possibilities that haven't been explored. And the approximate number system is a strong candidate for playing a role, because kids have figured out by that point, by age 5.5, that counting is related to approximate number. And they can estimate relatively large sets. They can judge that some numbers are greater than others on the basis of approximate magnitudes. So it seems like a good candidate.
Who's next? Anybody?
Oh, so I'm going to jump in. I'm going to jump in. So I believe that he has a meeting that he is late for. So it's already 2:40. So.
Oh no, you better start your meetings.
Yeah.
Right?
So let's end it here, I think.
So I think who's next? Alan?
Oh no, I was going to say that he should run to his meeting. So we're going to end this. And I believe you have a meeting with him later on, correct, Rochelle?
Yeah, fine. I was just want to say something about a number of infinities that might be of interest to Mark and others, but that's fine. Which is, from Cantor, you get the notion of one-to-one correspondence on every other number. So, yeah, but you run a test like that on kids, if you show it to them, but there's one-to-one correspondence, to say fine. But then you point out that you're pairing 1 with 3, etc. Oh no, that's not possible. Well, that's a really formal concept.
So I think Dave left. So.
Rochelle?
Yeah.